Every weekday, millions of kids step onto bright yellow buses, and most parents hardly give it a second thought. But here's the surprising part. In 2025, children are still about 70 times safer riding a school bus than riding in a car. This is the standard NHTSA and industry comparison. School buses transport millions more children while producing far fewer fatalities than cars. That's not chance. It's deliberate engineering. But how does a vehicle with no airbags and often no seatbelts accomplish this record? To answer that, we'll trace their history, their structure, their seating design, the technology that supports them, and even the people and rules that guide their daily use. Understanding how these buses became the safest ride for kids means starting with what came before them. From kid hacks to steel fortresses. It's strange to imagine now, but the buses we know as bright yellow steel fortresses began as little more than wagons on wheels. In the late 19th and early 20th centuries, many children rode to school in horse-drawn carriages nicknamed kid hacks. These wagons were simple and cheap, long wooden platforms with benches tacked along the sides, open to wind, rain, and snow. Their only purpose was to fit as many children as possible in one trip. Protection was never part of the design. A few boards separated them from the ground, and a jolting ride down uneven farm roads was simply the norm. Parents loaded children in any way, because at the time, transportation was measured in terms of convenience, not safety. When engines replaced horses, the design barely improved. Districts began modifying truck frames by attaching crude wooden cabins on top. These vehicles stood unnaturally tall and narrow, rocking unsteadily as they rolled along dirt and gravel roads. Their high centers of gravity made even mild cornering dangerous, and rollovers were common. Inside, there were no reinforcements. If one of these early buses tipped or skidded into trouble, wood splintered apart, metal tore loose, and children were fully exposed. And with no design standards, every manufacturer cut corners differently. Some stronger, many flimsier, and none built with real protection in mind. Beyond instability, fire posed a constant lethal risk. Fuel tanks sat against the outer body, right where collisions could rupture them. Seats were stuffed with flammable material, and a leaking line or small spark could sweep through the cabin before anyone escaped. Roofs, thin and poorly braced, collapsed quickly in heat or impact. Exits were sparse, often limited to a single narrow door, leaving dozens of children trapped in emergencies. Rollovers and fires weren't rare or abstract dangers. Accidents killed students outright or left stories of gruesome wreckage in local newspapers. Families of the period were aware of these risks, yet most placed their trust in vehicles that were essentially wooden crates balanced on wheels. That situation began to change as tragedies accumulated. Accidents that made headlines pushed school administrators and communities to demand more accountability from builders. Still, for many years, bus safety depended almost entirely on a district's budget. Wealthier communities could pay for sturdier, more enclosed bodies, while poorer rural areas often relied on whatever cheap models were available. For one child, riding to school might mean a relatively robust vehicle. For another, it was little different from the horse-drawn wagons of a generation before. Safety was uneven, inconsistent, and often an accident of geography. Early standard-setting efforts appeared in the 1920s, with tentative requirements for sturdier seating, defined entry and exit doors, and driver enclosures. The most pivotal moment arrived in 1939, when a national conference brought manufacturers together and finalized sweeping measures under the guidance of Dr. Frank Sear. That meeting did more than create paperwork. It locked in benchmarks for everything from roof structure and emergency exits to the now iconic color chosen for visibility. School bus yellow was no accident. It was scientifically selected to stand out in virtually any light or weather, making buses more noticeable on roads filled with dark, muted cars. This was a turning point. Passenger safety finally gained equal weight with efficiency and cost. From that era forward, the engineering philosophy shifted. The bus was no longer an improvised shell sitting on a truck frame. Designers began building with steel reinforcements, heavier beams, and specialized floor and roof supports. Windows were shrunk and strengthened to resist shattering. Emergency exits multiplied, at the back, along the sides, and eventually above, so there was always a way out. Fuel tanks were isolated, shielded, and placed away from routine collision points. These were deliberate answers to the disasters of earlier decades. Fires once fed by flimsy designs now met reinforced barriers, rollovers that once splintered a wooden cabin were slowed by the strength of a steel cage. The scale of the problem made these changes urgent. Today, nearly 25 million students ride school buses daily. That volume highlights why every improvement matters. For each rider to reach school and back home safely, design needed to anticipate rare but devastating accidents, and regulations had to make safety uniform across wealthy districts and cash-strapped communities alike. The reforms of the 1930s and 1940s began that process, and each generation of buses since then has built a tighter web of protection around its passengers. Looking back creates a striking contrast. On one hand, the kid hacks offered nothing more than planks on wheels. Early motorized models were unstable, fire-prone boxes cobbled together from spare materials. On the other hand, today's buses have been hardened into massive boxy machines that look slow and unglamorous but carry an unmatched safety record. They are reliable for reasons parents rarely see: redundant exits, tucked-away fuel systems, reinforcements hidden under painted panels. All of it arose not from marketing flair, but from decades of responding to disaster and folding each lesson into the next round of designs. In the progression from fragile wagons to reinforced giants, the critical shift has always been structural. The old designs gave way to buses built like frameworks on wheels, in which force is controlled instead of allowed to collapse the body. The knowledge that earlier generations lacked about crash dynamics, fire behavior, and rollover stability was eventually built into every beam and joint. Those decisions, one layer at a time, turned the school bus into a vehicle defined not by looks or speed, but by resilience. And yet that leaves one essential question. What, exactly, makes them so able to withstand impacts that crush smaller vehicles? To answer that, we need to take a closer look at the hidden design that holds the entire bus together. The steel skeleton secret. What makes a school bus survive crashes that flatten smaller cars isn't obvious from the outside. To most people, it looks like a giant box on wheels. Yet after severe collisions, photos often show buses still standing tall, their frames intact even when glass is shattered and panels are bent. The explanation lies in an internal framework hidden beneath the paint, a rigid steel skeleton that holds the passenger space together when everything else is under extreme stress. Unlike cars that depend on outer shells to manage crashes, buses rely on this internal cage to keep the cabin from collapsing. The way cars and buses approach safety is almost the opposite. Passenger cars use crumple zones, those thin front and rear sections designed to bend and fold on impact. They work because energy gets absorbed before reaching the people inside, and airbags and restraints handle the rest. But this kind of design has limits. When a car flips, the same pillars and roof rails that were meant to protect start folding inward under the vehicle's weight, forcing the cabin down onto occupants. Bus engineers didn't want that trade-off. Instead, they built around thick beams that are locked into a cross-braced system. In a crash, the frame doesn't give up sections of itself. It spreads the pressure across the entire skeleton so that no single piece has to fail. It's easier to picture using a simple comparison. Think of a soda can versus a steel bridge. The can is light and made to crush easily, which is fine if you need a container that absorbs force. A bus is more like a bridge, rigid, connected, and able to pass loads smoothly across multiple supports. For buses, that means when a side or the roof is struck, the force doesn't stay local. Stress is transferred into the vertical beams, then into the frame beneath the floor, and onward throughout the body. The shape resists caving in because every part is tied to the next. And remember, many school buses weigh up to 15 times more than a typical car. That greater mass usually means crashes stretch across longer deceleration times, so forces get distributed more gradually instead of spiking through the passenger space all at once. That's why accident images of school buses often show a recognizable outline even in severe rollovers. The windows break, the side panels deform, but the tall rectangular cage remains upright. The extra ceiling clearance above the seats acts as a buffer, so even if the bus tips over, children aren't immediately pressed against the ground. The reinforced skeleton keeps the roof from buckling, leaving escape routes open and preserving enough space for movement. It transforms a catastrophic rollover, one of the deadliest events in passenger cars, into something survivable. Weight also shapes why engineers chose rigidity over crumpling. A bus isn't just heavier than an average car, it's massively heavier, with enormous momentum on the road. Designing crumple zones thick enough To absorb those forces would require impractically huge amounts of material. Instead, engineers leaned on the strength of a welded grid that resists collapse. The rigidity protects the cabin by refusing to give way, and the vehicle size spreads out the energy so children inside experience less violent jolts. Put simply, it's safer to prevent the collapse entirely than to let the frame crumble and hope the padding or restraints make up for it. This approach goes further than surviving once a bus rolls. It helps prevent rollovers from happening in the first place. Tall, boxy vehicles tend to tip under sharp or uneven forces, but with a cage tying the top, sides, and bottom into one solid block, the structure resists twisting. When one side lifts, the skeleton pulls against itself, sharing the weight and reducing the chance the bus will topple. That design choice makes buses more stable on winding rural roads or fast lane changes than their height alone would suggest. Stability is a safety feature. Keeping a vehicle from flipping removes the riskiest type of crash before it starts. Side impacts also reveal why buses stand apart. In cars, doors and windows are weak points. Another vehicle striking from the side can break through with little resistance, leaving occupants exposed. Arrive at the side of a bus and you'll find tightly spaced steel posts bracing the walls like a grid. Behind the painted panels, these beams form barriers that prevent intrusion. They don't necessarily stop dents or broken glass, but they stop the cabin from collapsing inward. You can think of it like scaffolding behind a facade. Even if the surface breaks, the structure remains upright. The difference between cars and buses becomes sharper when you imagine the crash forces step by step. In a car rollover, one roof support takes the brunt of the force until it buckles, then the load concentrates onto the next, and soon the structure folds completely. Occupants are pinned before seatbelts or airbags can matter. In a bus, the opposite happens. One beam takes tension, passes it immediately to its neighbors, and the whole cage shares the stress. By the time it settles, dozens of bars have absorbed and dispersed the energy, and the cabin shape stays intact. It's not glamorous design, but it saves lives by preventing collapse long enough for passengers to escape. Parents mostly see the glossy yellow sides and broad windows when a bus drives by, but beneath that is a carefully engineered barrier system. The painted metal panels act as cosmetic skin and initial contact layer, while the skeleton underneath serves as the true armor. That's why in many crashes buses remain upright and recognizable while other vehicles end up twisted beyond recognition. This hidden cage isn't just an invisible bonus, it dictates how the entire accident unfolds, steering energy paths away from the children sitting inside. The approach is unusual compared to most vehicles on the road. Almost every car is designed to crumple because adults are belted in, airbags trigger instantly, and masses are relatively low. A flexible frame makes sense there. For buses, with dozens of unbelted children in one compartment, energy absorption inside the cabin would be disastrous. If the frame gave way, the seats themselves wouldn't matter. Children would be trapped in a collapsing box. Rigidity is the logical alternative. By making the whole vehicle act as one brace system, buses turn their size into the very thing that protects their passengers. Of course, that rigid skeleton is only one part of the safety package. Other details, from the way the seats are built to the way emergency exits are arranged, only work because that frame protects the surrounding space. Without the cage, those measures would collapse along with the cabin. But with it, the structure stays intact long enough for the rest of the safety systems to matter. That skeleton matters, but it only solves one set of problems. Next, how we keep kids inside that safe space without buckles. Why no seatbelts isn't neglect. One of the details that surprises most parents when they first step onto a school bus is what they don't see. In family cars, every passenger has a seatbelt, airbags hide in the dash, and the expectation is that safety comes from strapping in. On a bus, it looks the opposite. Rows of tall padded seats line the aisle, but no buckles click across laps and no airbags wait to deploy. For many families, this feels unsettling, almost like an oversight. But what looks like missing equipment is actually intentional. It reflects a design philosophy unique to buses, one built around the principle of compartmentalization. Compartmentalization shifts the role of protection away from belts and airbags and into the structure of the seating itself. Each seat back rises above a child's head, is thickly padded, and sits only a short distance from the next row. In the engineering model, children don't need to be strapped in place, instead, They are surrounded by cushioned surfaces meant to absorb forward movement. If a crash occurs, momentum carries them into the padded back in front of them rather than into a hard surface or piece of equipment. Each row doubles as a soft barrier, turning the cabin into a repeating series of compartments that insulate children from violent impacts. The seats work in more sophisticated ways than they first appear. Rather than acting as immovable walls, the frames flex slightly, releasing energy when struck. That controlled give reduces shock in the same way a spring reacts under pressure. Spacing is carefully measured. Openings are close enough that children can't build dangerous speed before striking the seat ahead, but not so tight that legs are cramped. The high padded backs ensure the torso, not the head or neck, bears contact with the cushioning. Put together, the elements mimic a cocoon effect, a passive shield engineered to manage how young bodies move during a collision. The principle feels counterintuitive because most parents compare buses to cars. In a car, no seatbelt means serious risk. A sudden stop sends bodies into dashboards, windows, or worse, out of the vehicle. On a bus, though, physics shifts the equation. Weight is the biggest factor. A full-size bus can weigh 10 to 15 times more than a family sedan. That much mass doesn't stop suddenly. It decelerates over longer intervals. When crashes unfold, the change in speed is stretched out, lowering the forces inside. Children may tilt or slide forward, but the contact is slow enough for padded seats to absorb effectively. That difference in momentum explains why restraints are essential in cars but not the cornerstone of safety in buses. Recognizing how this works can alleviate some discomfort but not all of it. Parents still worry about the flexibility children have inside the cabin. Standing, leaning sideways, shifting around. Compartmentalization is most effective when riders stay seated properly. And that is where skepticism re-emerges. Why not include belts anyway, as backup? The answer is layered. Installing them could make rides less safe overall if children misuse the restraints. Younger students may place belts incorrectly across necks or stomachs, creating its own dangers in sudden stops. Older students sometimes ignore them entirely. Unlike cars, where adults are present to correct misuse, bus drivers cannot check dozens of children across multiple rows without distracting from the road. Another complication is how restraints affect capacity. Adding seatbelts tightens spacing, often reducing the number of passengers per bus. That forces districts to run additional routes or move more children back into family cars, statistically far less safe. Industry analyses and federal discussions also underscore the logistical barrier. Retrofitting an entire nationwide fleet would be extremely costly and complex. For many cash-strapped districts, that expense diverts funds from broader safety measures that benefit every bus on the road, like reinforced structures, extended mirrors, or driver training. Still, some states have chosen to add belts under certain conditions. A small number, including California, New York, New Jersey, Florida, and Texas, require lap shoulder restraints on specific types of buses, with variations tied to funding or vehicle size. These rules reflect ongoing debates more than consensus standards. Investigators such as the National Transportation Safety Board have acknowledged that while compartmentalization protects well in common frontal crashes, lap shoulder belts may improve outcomes in side collisions or rollovers. The measures are not universal, but they illustrate how policies evolve as research grows. The science behind compartmentalization also extends beyond crash forces. Consider what children can strike inside a bus. In a passenger car, an unbelted rider risks colliding with glass, door frames, consoles, or steering wheels. In a bus, interiors deliberately remove those hazards. Surfaces have padding, corners soften, and exposed hardpoints are minimized. Nearly all motion funnels forward into seatbacks designed for that purpose. This regulation of space is what makes a restraint-free system viable. Children meet only surfaces engineered to absorb them. At the same time, experts recognize that no system is perfect. Compartmentalization works best when buses remain upright and stops are frontal. Severe conditions, like heavy side impacts or complete rollovers, test its limits. That's why the conversation around belts hasn't disappeared. But every push to install them runs into the reality that transport safety is not only about equipment, it's about practical application. Making a safeguard reliable means building it to work even when children forget instructions, ignore guidelines, or rush off the bus in distraction. Compartmentalization meets that test by requiring no active participation from passengers. For decades, statistics have reflected the success of this approach. Year after year, data show that school buses, without belts, carry millions of children with dramatically fewer fatalities compared to private vehicles where belts are universal. The consistency of those numbers argues that the philosophy of protecting children through structure, mass, and seat design is working. What looks strange, even risky at first glance, reveals itself as a different solution to the same problem. In the end, the absence of seatbelts is not neglect but an intentional trade-off. Engineers designed these buses assuming young passengers can't be counted on to strap in properly every time, but they can be surrounded by cushions, beams, and compartments that never forget their role. The outcome is a safety system built into the cabin itself, one that doesn't rely on perfect behavior to function. Families riding the familiar yellow buses each morning rarely think about steel cages or compartment padding. What stands out most is the appearance of the vehicle itself. That look is no accident either. Choices about how a bus catches the eye are as vital as the unseen framework inside. And the next safety feature works before a crash even happens. It ensures that the bus gets noticed in the first place. The science of the giant yellow billboard. If there's one feature of school buses that nobody overlooks, it's the color. No matter the state, no matter the district, they all share the same unmistakable bright yellow body. That choice wasn't a stroke of stylistic branding. It was established as a national standard at the 1939 conference that set the foundation for bus safety rules. Researchers at the time had identified that yellow is one of the quickest colors for the human eye to detect in low light. That one insight turned into a requirement that has outlasted nearly every other early regulation, because visibility remains a tool that prevents accidents before they unfold. The science behind that choice is deceptively simple. Our eyes respond differently to each color in the spectrum, and yellow sits in a range that the retina identifies rapidly even when light is fading. Compared to darker car bodies or road surfaces, the painted bus surface jumps out of the visual field almost immediately. That reaction time, measured in fractions of a second, may not sound like much, but at highway speeds, a fraction of a second equals dozens of feet of extra time to hit the brakes or steer away. The result of standardizing that hue was measurable. By making buses detectable from farther away in fog, rain, or pre-dawn hours, the chance of drivers noticing them in time to avoid mistakes improved dramatically. Unlike aesthetic paint jobs that reflect preference, the shade known as school bus yellow is carefully defined so it performs consistently against almost any backdrop. Whether the vehicle is parked against snowbanks, traveling through wooded highways, or idling in misty early mornings, its surface contrasts against its surroundings. That consistency ensures that drivers don't just see a vehicle, they register a priority object requiring caution. If the paint were darker, muted, or varied from place to place, that instant recognition would vanish. Instead, uniformity provides an early warning system to anyone sharing the road. That gives the paint job an unusual status among bus safety measures. Steel cages, energy-absorbing seats, and updated brakes all protect passengers in a crash, but the color works upstream of all those layers. It reduces how often those other defenses are even needed. From a cost-benefit perspective, a coat of standard yellow paint is one of the simplest adjustments ever mandated in transport design, yet its payoff is seen in accidents prevented before they can happen. Consider how this plays out in ordinary daily use. In midwinter, children often meet their buses while it's still dark out. Rural highways may wrap in fog or heavy rain, where headlights alone can blur into diffused halos. The yellow surface breaks that haze in peripheral vision, drawing the gaze of an approaching driver before conscious recognition sets in. On side roads, at intersections, or when emerging from a driveway, that split-second recognition creates space to brake, pause, or give way. It's an advantage that lights and reflective panels reinforce, but the base color is already doing essential work in advance. Psychology supports it as well. Drivers share a learned association. Yellow signals demand attention. Road warning signs, traffic lights shifting to caution, and hazard markings all rely on the same color. A large yellow shape approaching in traffic becomes part of that system. Drivers may not think the words school bus, but their brains trigger the same reflex built for warnings. Slow down, prepare to react. That familiarity makes buses visible not only to careful drivers but to distracted or drowsy ones. Even inattentive eyes are more likely to catch yellow than filter out muted tones blending with the environment. It helps to see how unusual buses are in this regard. Personal vehicles come in colors chosen for appearance: black, silver, blue, none designed with detection in mind. Trucks and vans often match company livery, again relying on stylistic branding rather than visual performance. The bus ignores preference completely. Every district, private company, and manufacturer paints vehicles in the same color because attention, not aesthetics, is the priority. Taken together, the effect can start to look like a mobile fleet of warning signs moving daily across cities and towns.